Yaskawa.
Welcome to the Sigma-5 Indexer e-learning module. The topics of this training fall into three sections. First, a product overview, then a simple example, and finally a top-level explanation of some of the additional features. Let's start with the overview material for the indexer and see how the device fits into a motion system, what connections are on the front panel, the file system, and the programming concept. The Sigma-5 indexer is an option that gives positioning capability to the Sigma-5. Your positions are stored in the indexer as well as the motion profile constraints. You can also specify repeats and delay times and output status for each move, but the indexer moves the motor only when commanded by an upper-level controller like a PLC. The PLC can request the positions using either digital inputs or serial commands. You need the PLC for logic and timing because while the indexer does have what we call the program table, it just stores the moves and the indexer does not make decisions by solving logic or writing to any variables. Here's a more detailed illustration of the system configuration and the basic connections between the PLC and indexer. One input controls the indexer operation mode, which will be either program step mode or manual, jog, and homing mode. Most of the time you'd be in the step mode. The particular program step number is selected by the PLC using 8 digital inputs. The value of the 8 inputs is read as binary, and the decimal conversion determines the step number. For example, if select 1 and select 2 are on, that's binary 110, which is 6 in decimal, and therefore selects program step 6. And this means that execution of the program table will start at step 6 when the start-stop input goes on. So you can see how the PLC can choose any of the 256 program steps by turning on the correct select inputs. After motion starts, the in-position output will be used to signal the PLC to indicate that the motor has reached the final position. This in-position is critical for the PLC to sequence other events, and it also means that no encoder wiring is needed between the PLC and the indexer. Just use in-position. So these are the basic control connections and the basic operation of the indexer. The indexer can also be operated by a PLC over serial commands using RS-422 or RS-485 communication connected to port CN12. Network communication like this dramatically reduces the I/O wiring points, especially if several indexers will be wired to the PLC. Up to 16 indexers can be connected on one RS-422-485 network. The command set is simple, comprising of roughly 100 ASCII commands. As in the previous example with discrete I/O, to start at program step 6, the ASCII command is 1start6. The indexer responds 1 OK to acknowledge receiving the command. All the commands and responses can be monitored in the SigmaWin Plus software. It is also possible for the PLC to start a customized move without using the program table at all. And this way you'll have virtually an unlimited number of speeds and distances, which would first be calculated in the PLC and then streamed to the indexer. So as the application requirements change, the moves can change without reconfiguring the indexer's program table. Let's take a look now at the Sigma-5 indexer front panel. You see the standard power supply inputs for line power, L1 and L2 and L3 for 3-phase. Line power simply charges the DC bus and the lamp indicates the charge level. Control power, L1C and L2C, turn on the logic board, including the I/O, the display, the indexer card. The display reads out the alarms, warnings, and errors and has indicators for control power. But the rotary switches and dip switches are not used with the indexer. Terminals B1, B2, plus and minus give you access to the DC bus and for connection of regeneration resistors. Then at the bottom you have 3 motor phases, U, V, W, and the ground, with the encoder at CN2 and the safety at CN8. The connector CN3 is for the handheld digital operator, but it's much easier to configure the indexer through the CN7 USB port using our SigmaWin Plus free software. I/O is accessed through two connectors, CN1 for amplifier functions like overtravel, home sensor, registration latch, while the CN11 connector on the option card handles the discrete I/O to the PLC. Finally, we have the serial connector CN12 for serial commands over RS422 or RS485 protocol. The indexer is configured using Yaskawa's free SigmaWin Plus software, which generates up to 4 separate files. You have parameters, program table, zone table, and jog table. The most critical of these is the parameters file, which defines all the configuration options, units of motion, and homing methods. The program table is also critical as it stores the positions and move profiles. The zone table and jog table are used only if zone and jog functions are implemented. So it's very important to understand this concept of the 4 different files so that you can keep track of and organize each of these for maintenance and troubleshooting purposes. I have referred a few times here to the program table, so let's take a quick look at it, and in the next section I'll do a simple step-by-step example. Each program step in the program table is a row, and the columns define the move profile for that step. You have position, speed, XL decel, output state, and the event that marks the end of the step. Loop allows a single step to be repeated a number of times. For example, as it shows here, to repeat an incremental move 3 times in a row. And a delay time between the steps can be included in the event field. The next field lets you sequence different steps together, for example, to move back to the starting position after the 3 incremental moves. 2 fields for the registration capability define the speed and distance with which to correct the original move after a printed mark is sensed on the product. And you can see that this is all very simple programming, if you even want to call it that. There are no variables, no logical expressions, and no looping of move sequences. The indexer does its job well, but it is intended to be used with a PLC for all but the most simple applications. Now let's take a look at a quick example of a new application. I'll outline the steps for connection and configuring the application parameters, the program table, and then I'll take it one step further and look at absolute positioning. For our application, let's consider a feed-to-length machine. The indexer will control the pinch rollers to repeatedly pull a length of material and then stop while a press makes a cut. The details of the application are a 25:1 gearbox, 4-inch pinch roll diameter. It pulls 14 inches at a max speed of 20 inches per second. Acceleration is limited to 100 milliseconds to maximum speed, and we need to stop for 500 milliseconds for the press to cut. We'll give a 100 millisecond pulse from the indexer's P out 0 output to signal the press, and the material has to be in position with a tolerance of 1/1000th of an inch. An important step for any application is to extract the pertinent information and make a sketch of the motion profile and I/O timing. So I've done this, and that way we'll have an easier reference on how to configure the indexer's moves. So here's the application, and I will refer back to this diagram as we proceed. The configuration I'll be using in this example includes a few switches and LEDs just to represent the PLC and for simplicity and demonstration. I have a switch for mode, a switch for start-stop, and I have switches for all the select inputs. And I also have the in-position outputs wired to an LED. SigmaWin Plus software, so I'll connect the USB cable and go online. The first step in the solution process is to use the setup wizard in SigmaWin Plus to define the units of motion based on the mechanical configuration of this particular machine. Then the second step is there are a few parameters to set within the parameter editor, such as the default move profile parameters and any other configuration options. The final step is to develop and test a program table that moves the motor according to these application requirements. And cleared all alarms. I've tested my I/O. I've reset the parameters to factory default. I've test run the motor, and I'm connected online, and I'm ready to go. And so here we go under the parameters menu to the setup wizard. I'll apply the default encoder and go ahead to the reference input setting. Click next for the gear details. And this system could be modeled as what they call here a roll feed. I'll move ahead and enter the roll diameter as 4 inches. And you see that the gearing is listed here as the ratio M to N. So that means the 25:1 means 25 goes here in the denominator. Next, and at the top you see the reference unit is the positioning resolution commanded by the indexer. And it's suggesting a pretty high resolution. Looks like 1, 2, 3, 4, 5, 6 digits past the decimal point. And these are the positioning units that we'll use in the program table. The result of this is to set what they call the electronic gear ratio. Those are pretty important parameters, and luckily we don't have to calculate them. That's what this whole wizard does for you. And then down below is the position completed width, which it has as 1 reference unit. And please note that this parameter corresponds only to the coin output. They're talking about the coin output here, not the in position output. But even so, I'll just match this up to what I expect for in position of 1/100th of an inch. And so if the reference unit is 6 decimal places, 1/1000th of an inch will be 1000. This coin signal, by the way, is important when you are tuning or tracing the response of the motor during the move, particularly when you want to measure the settling time. So I'll hit apply. And there are other settings here, other options here, but the reference unit setting is the main focus. That's really the only one you need. And so you can go to save write with a backup file. That backs up the parameters in there, which are default for me. And write them in and click OK. And you can even save this set then. Now I'll finish out of the setup wizard and confirm that. And it's important after you ever change parameters like this to go and cycle power or use the software reset button. Click execute. And anytime you do software reset, you should reconnect. And now we're back online with the mechanical system setup. Wizard, I'll go to the next step and look at the parameters themselves under Edit Parameters. And you want to find the option parameters, which will be in the tab here called Option. And all of the option parameters start with PNB. And just scanning through some of these, you see there's some communication protocols. We have some input mapping, some outputs over travels. And I don't have time to cover all of these, but one that's likely to require setting, and in my case I will set it, is the forward and reverse soft limit. That keeps the motor from even starting a move that it knows would be out of the positioning range. So to disable that, you come into the parameter PNB21 and set it to 0. 0 for forward, 0 for reverse. And now I've basically disabled that feature, and I'll talk more about that feature in the later slide of this presentation. Let me jump down now to parameter PNB2D, the in position width. I mentioned previously that the coin signal width is useful for graphing, and the in position width is a different parameter, and you want to set that to match the coin width so that your in position output back to the PLC will be set appropriately. So opening that up, we'll want the same amount as we'd had with the coin output of 1/1000th of an inch, which if you remember was 1000 reference units. And the final parameters I want to focus on for this application are the speed, acceleration, and deceleration. These are parameters that define the default move profile. And one thing you notice is that the unit of these for speed is 1000 reference units per minute, and the speed for acceleration and deceleration is 1000 reference units per minute per millisecond. And at At first glance, that seems like kind of a lengthy unit, but it turns out to be simply a conversion exercise. And so the speed I want is 3 inches per second, but instead of putting in 3, I'm going to put in 180,000 reference units per minute. I'll show how to convert this in the next slide. The acceleration will be 0 to 20 inches per second in 100 milliseconds, and in this unit it turns out to be 12,000 for acceleration, and we'll match the deceleration to 12,000. So you set those defaults for speed, acceleration, deceleration, the in position width, remove the soft limits, and I'll write these parameters in cycle power after this message. Close, software reset, and best practice as usual to reconnect. So let me explain how I came up with 180,000 for the default speed in PNB27. You can see it's basically a unit conversion problem to convert inches per second to 1,000 reference units per minute. In the wizard, we had set the reference unit, remember, to 6 decimal places. So you divide by the reference unit of 0.000001 inch to cancel out inches, and there are 60 seconds in a minute. Then you pull out the factor of 1,000 and you get the unit of 1,000 reference units per minute. So the answer is 60,000 reference units per minute is the same as 1 inch per second. That means that in this application we just multiply the speed of inches per second by 60,000. And so if I want 3 inches per second for the default speed, I'll multiply and get 180,000 for the parameter PNB27. And likewise for the maximum speed of 20 inches per second, I would multiply to get 1,200,000 reference units per minute. For acceleration, the motion profile requires an acceleration time of 100 milliseconds to the maximum speed, which we already know is 1,200,000 reference units per minute. So I'll divide this maximum speed by the acceleration time of 100 milliseconds to get the acceleration rate 12,000 thousands of reference units per minute per millisecond. And you can see that the units in this case work out pretty easily when you put in the acceleration time in milliseconds. So now let's open the program table under Edit Table, Edit Program Table. And we want to enter a basic 14-inch move, 14 inches relative distance. And the first question here is the step. What step to use? Remember, the step corresponds to the input combination for the select inputs. So step 0 means all the inputs are off. Sounds like a good place to start. And the first column here is position. So you go down here and choose the target position. Just quickly here, you see that you can have relative or absolute, and there's other options as well. Do relative distance, you put in the distance we want to go. We said 14 inches. So you start with 14, and then remember your reference unit. In our case, it was 6 decimal places. So add 6 zeros, and OK. So there we have got it. The next field over here is speed. And just like we put the default speed, we can now use that same unit. And if I wanted a slow speed of 3 inches per second, I put in that 60,000 conversion factor and get 180,000 for my speed. The next two columns are registration distance and registration speed. And if you're not using the registration input or registration functionality at all, just leave these alone. That's my condition. Acceleration and deceleration, I'm also not going to change. I'll just use the default that I already set in the parameter. And move on here now to P out. The important thing to know about P out is that it defines the output state of all the outputs during the move. And so you can see here each of the 8 outputs, 0 through 7, P out 0. Same as previous step, just leaves it alone. You can change it to either active, not active, or to look up the output state based on a zone table. I'll talk more about that feature. I would like this one to be non-active to be sure that this output 0 is off during the move. And then later on we'll have it turn on after the move. So click OK. That puts in the N here for non-active in the location of output 0. Event is important as it defines the condition that marks the end of the step. So very typically you'll have the positioning complete, meaning you're in position within that tolerance that we set previously in the parameter. And there are other options as well. You could set a near location, you could set reference out, the command is complete, any of the inputs also could be used, or just a straight time. Positioning complete, and an additional wait time if desired. We wanted 500 milliseconds, let's try that out. 500 milliseconds after the positioning is complete. You see he puts in a code for that, IT 500. Loop means the indexer can automatically repeat the whole step a set number of times without another start command from the PLC. And how about for this test move, we do 3 loops. That means 3 total moves. And the final column, next, allows you to build a sequence of steps, again without relying on the PLC, and we'll try that out later. So here's something very simple, little program that we want to test before we get too far into it. Notice the green highlight indicates that this data has not been written into the Sigma-5. So you hit write, and it's warning you that when you turn off the power, you will lose your changes. So this is a temporary write to the RAM of the Sigma-5. And so the idea here is that you make your changes, write them quickly to the RAM, and then if you want the change to be permanent, you save it, and that saves it to flash permanently. So that makes the change survive a power cycle. And so now the indexer is configured, as long as we don't do a software reset or cycle power. And we can close the program table. From the PLC, in my case I have easy control here with switches, but in any case, first step would be to turn on the servo. You can see I've checked the appropriate boxes here in the output and input status monitor to confirm that SI0 is turned on the servo, so let's turn that on. And you can see that goes from high to low. As a confirmation output back to the PLC, you can use the brake output, and if you watch the brake output, that also goes to low to release the brake when the servo's on, if you did have a brake motor, and if not, it's just a good confirmation signal. Servo off, servo on. The next step is to turn on the indexer's mode input. So mode went from high to low, that means it's on. Now before you hit start the program, you want to check your select inputs are all selecting step 0. See, all of them are high. High means off, and therefore step 0 is being selected. And so now I'll activate the start stop input. And you can see as the motor runs, you'll get in position turning on when the move is done, going from low to high. So the motor did its 3 moves, and we are finished in position. Now I'd like to show a few troubleshooting tips for the Sigma-5 indexer. And your main troubleshooting area will be in the motion monitor, which you can get under the monitor menu if you don't see it, motion monitor. And scroll down to the bottom, and you can see that the program step here can be monitored. Right now I'm at step 0. You also have some distance and position information, but you also have this error monitor. Now an error code is a bit different than what you might be used to in Sigma-5 with the alarm monitor available here in the system monitor. It turns this box red, shows you the alarm. Your alarm output would go from low to high, and the servo will disable. But a programming or logical error, such as I've accomplished here with the servo on incomplete error, I try to run the program with the servo off, I get this error monitor E54E, servo on, incomplete error. And so that does not show up in the alarm monitor. It will, at the time of occurrence, set the warning output from high to low momentarily, and you'd see the alarm A9F on the panel of the amplifier if you're looking at it. But this error monitor is the only place to see that code within SigmaWin Plus. If you do want more information on the error code, I recommend you look at the PDF of the indexer manual, and a real quick search for that code will give you more information at E54E. And you see here the servo on incomplete, and it gives you a lot of meanings and corrective actions. And so I think in this section, section 9 troubleshooting of the manual PDF, you get a good idea of what to do based on the error code description. Well, I have the basic 14-inch index move for my application working. It's not running at full speed, and the I/O timing's not quite right. So I'll show here how to link a sequence of steps to control the output timing, and then how to repeat that sequence. First, let's correct the move that's in here from 3 inches per second to 20. 20 inches per second was 1,200,000. And now how can I get this P out to turn on at the end of the move for 100 milliseconds? Remember that the P out column determines the output status during the whole move from beginning to end. So the answer is to use a separate program line that does not move the motor but only changes the output. So for step number 1 now, I can change the target position to without reference, set the output to active, and put a wait time of 100 milliseconds. Now I do have to still correct the move above here. I'd have to put the loop number back to 1, and I don't want to wait 500 milliseconds before I turn that output on. So I'll set the wait time here to 0. And to link these together, I'll use the next column and uncheck complete and put in step number 1. But this is still not done because what about that 500 millisecond wait time? Well, I'll add another line, set it to without reference, and have me wait for the balance of 400 milliseconds with the output off. And link step 1 to step number 2. Now you can see I have a sequence of 3 steps. And it's important to note that the indexer cannot repeat this 3-step sequence a set number of times. The loop applies only to that particular step, not to the sequence. So logic for looping a sequence like this corresponds to the PLC. Now I could make an infinite loop by taking step 2 and linking it back to step 0, but then the PLC would have to pause the process if it wanted to stop. Either way, the PLC is involved, and I think it's going to be better programming practice to let the PLC start the motion rather than interrupt and cancel an infinite loop. So I'll write this into the indexer. And by the way, it's important that when you hit write, you check that the start, stop, home input is high. You don't want to have a program running when you try to send data down to the RAM of the indexer. And I'll close this program table. So let's try out the final move sequence here. The servo is on and I'm ready in mode 0. But this time I'll take a data trace so you can see the motion here before I hit start. So you go to trace and I'll set it up with a position reference. Hit the set button and I'll put the sampling time here to 1500. And then I'll hit start before I activate the start-stop input. And I get a data trace of this move. I can see the torque, the speed, the commanded position. You don't get to see the programmable outputs, but you do see the motion, and you see the coin signal represents the in position bit. And so it looks like the move is good. Now let's add an absolute move. I'll go here to step 8. You see that the target position can also be absolute position as opposed to relative or incremental distance. We've been doing relative or incremental moves here because it didn't really matter for our application where the motor was or where it ended up on a coordinate system. It just had to move 14 inches and pull that material continuously in a single direction. So for this absolute position to make sense, we'll need to move away from that particular example and consider an application where you have a limited travel and you may need to move back to a specific position. For many applications, it's so much easier to think of different points within the movement of that machine as opposed to incremental distances. But in order to use that, you have to know the machine's position 0. So let me put in here an absolute move to that position 0. Choose a slow speed here of 60,000 reference units, and I'll write that in. This will be the end of my program, so I'll save. That puts it permanently into flash so I can cycle power. And now I can close this. So I'll cycle power with the software reset. And I'll follow the caution and reconnect. And now after I cycled power, I can see down here what my position is. And an incremental encoder after you cycle power will be at position 0. And you may then need to home it to be sure that it truly is at position 0. I'm not at position 0 because I have the absolute encoder motor, which retains the position during a power cycle. So either way, you have to establish the 0 position. Before you use an absolute move, you've got to establish the 0 position. The way you find the 0 position depends on the type of encoder you have, if you have an incremental encoder or if you have an absolute encoder. For an incremental encoder, you find the 0 position using what's called a homing routine, which would be executed every time you power up the machine. And a homing routine usually involves moving that axis slowly until a sensor is found, and then you establish that as the 0 position. If your motor is the absolute encoder motor, then you just have to do a one-time 0 position calibration in order to define the starting point, and you don't have to use a homing routine. That's the whole point of the absolute encoder motor, is to avoid a possibly lengthy homing routine. The absolute encoder is the Yaskawa standard option for Sigma-5, so you're likely to have the absolute encoder, and you'd have to follow these steps to establish the 0 point position. You start by moving the axis to the 0 position, then you zero out the offset parameter, PNB25, initialize the encoder, and then set the offset parameter to the negative value of the current motor position. This calibration is one time, but you would have to repeat it after any maintenance that results in a disconnection between the motor shaft and the load, or if you initialize the absolute encoder for some other reason. Some examples of the situation are replacing a coupling, gearbox, replacing the motor, replacing the encoder battery with the power off, or having disconnected the encoder cable from the motor. So any maintenance items may require you to redo the absolute encoder calibration. 0 position with the Sigma-5 indexer. So I've moved the axis to position 0 and I have the servo off. I can see the feedback position is not 0. Open parameters. And under option, I can go down to PNB25 and I see that there is no offset being added to that position either. So if this parameter is not 0, at this time you'd want to set it to 0 and write that in. Leaving parameter editor, go to the setup menu and reset the absolute encoder because this current position offset is too big. I'll go to reset absolute encoder, walk through that, then cycle power. You can see already that the motor position has been updated as resetting the absolute encoder erases the multi-turn data. So we now have the position within 1 revolution. Click OK here. It says to reconnect. I'll do that quick. So now I'm at 0 position, and the idea is to cancel out this feedback absolute position with the offset. So I'll go to my parameters again. Go to PNB25 and set the offset to the inverse of the current motor position, -207,795, matching this number here. Okay, you write that in. It says you have to cycle power. Close that and software reset. And now I am at position 0 on the axis. My motor current position is reading in 0. Then just as a reminder, in the program table, if I ever need to come back to this position, which is now position 0, I would simply in the PLC execute program step 8 to go to position 0. And that is how you calibrate the absolute encoder for position 0. The final segment of this training is to overview some of the advanced features of the Sigma-5 indexer. And for these, I'm not going to demonstrate how to use these features. I'm just going to give an introduction to each of them. First is homing. If you have the incremental encoder, then the axis position goes back to 0 at every power-up. If that behavior is okay, then you don't need homing. But usually it's not, and so it's common to run the machine through a homing sequence in order to find a repeatable starting position after every power-up. The indexer includes 3 built-in homing methods. It can find the C pulse on the encoder, it can look for the sensor input, or it can have a combination of both. Homing cannot be executed on a motor with an absolute encoder. The absolute encoder simply requires the one-time calibration using the parameter PN-B25 as previously demonstrated. And the way that the absolute encoder works is the battery maintains power to the encoder while the power is off. If you have an absolute encoder but do require homing routine anyway, you can turn off the absolute functionality in the parameter PN002 and then use a homing routine. And if you use the absolute encoder in this way, meaning use absolute encoder as incremental, then you don't have to have the battery for the absolute encoder. The indexer also supports registration positioning, and registration means that the move distance and speed can be changed based on a printed mark on the material being moved. For example, maybe expect a 14-inch move, but a mark is printed exactly 3 inches before the end of the move. So for correct positioning, once that mark is sensed, you can forget the original 14-inch move and simply move the remaining 3 inches. This is the registration distance. Registration ensures that the index move remains synchronized with the material. And this feature is especially important for the feed-to-length type applications where the material or the product is moving forward continuously, because without registration, even the slightest variance in the product will end up accumulating over time. The indexer uses a dedicated high-speed latch input for the sensor called RGRT, located on the CN1 connector of the amplifier, so that the exact position of the mark is captured every time. Some applications benefit from zone outputs. Another name for this feature, zone output, is also PLS, Programmable Limit Switch. The idea is to establish predefined positions in the movement range where a particular output is on or off. These position ranges are stored in the zone table ahead of time. The benefit to using the zone output is that you have a high-speed feedback back to the PLC instead of using sensors. If you want to know where the load is, you just use the encoder rather than using sensors. The indexer has the capability of running in jog mode at any of up to 16 speeds. The speeds are selected using 4 inputs, with an input for positive jog and an input for negative jog. You store the speeds in the jog table. And the purpose for Jog Operation is simply a way for the operator to manually move the machine during times such as maintenance, troubleshooting, or calibration. The Sigma-5 indexer also supports software limit functionality. Software limit functionality defines a maximum and minimum position to the range of motion for the linear moving axis. Now, software limits don't replace hardware level over travel sensors, but instead they're a level of protection, basically, against miscalculated commands issued from the PLC. A software limit prevents the axis from attempting a move that would put the machine outside the allowed positioning range. Rotary machines require some special attention with indexing applications because positioning can be accomplished by moving in either direction. Consider, for example, a rotary table with positions from 0 to 360 degrees, where 0 and 360 are the same position. You can think of this as the rollover position. Because of this rollover, a rotary load can reach the final position by traveling in either direction. The indexer has a rotary moving mode parameter, PN-B20, and it can figure out automatically how to accomplish these absolute positioning moves, either forward, reverse, or to move the shortest way. A rotary load also implies that some absolute positions are out of the logical range. In this illustration, there is no position greater than 360 or less than 0. The software limits are used in the rotary applications in order to establish this range and the rollover point. Although the indexer is a simple positioning device, this ability to intelligently handle the rotary movement is quite powerful and makes it really easy to integrate then with a PLC. This concludes the Sigma-5 Indexer Introduction e-learning module. I wish you success with the Sigma-5 Indexer, and remember to contact us by email, web, or phone for further information.